So we are going live right now.
Good.
And we are live.
Okay.
So hello everyone. Hello to all our viewers who joined us on the YouTube. We'll just start the talk in a few minutes. So hi everyone, hello, good afternoon, and welcome to the first episode of SciTalks. I hope you're all doing well. So SciTalks is an initiative by the Science Council of IIT Bhopal, and it's an online live talk series by eminent scientists across the country who will talk to you about their research every other weekend. So welcome to the very first episode. We are very fortunate to have our first guest this afternoon, who's been kind enough to accept our invite, Professor Shiraz Minwalla. Professor Shiraz Minwalla works at the Department of Theoretical Physics at Tata Institute of Fundamental Research in Mumbai. He graduated from IIT Kanpur and got his PhD at Princeton University under the guidance of Dr. Nathan Seiberg. He then worked at Harvard as a junior fellow, then as an assistant professor before moving to TIFR, where he works right now. And his primary area of research is string theory and quantum field theory. Accolades for his work, some of which include the Swarnajayanti Fellowship, the ICTP Prize in 2010, the Shanti Swarup Bhatnagar Prize for Science and Technology in 2011, the Infosys Prize in 2013, and quite recently he received the New Horizons in Physics Prize for, I quote, his pioneering contributions to the study of string theory and quantum field theory, and in particular his notable work on the connection between the equations of fluid dynamics and Einstein's general relativity. Professor Minwalla's talk today is titled The Search for Quantum Gravity. To all our viewers, please feel free to ask your questions on the YouTube live chat, and we'll read them out to Professor Minwalla at the end of his talk. Professor Minwalla, it's a pleasure to have you here. How are you doing?
I'm fine, thank you. It's good to be here.
Glad to have you. Let's start with your presentation, sir.
Okay. So hello everyone. My talk today is titled The Search for Quantum Gravity. According to plan, the presentation itself will last maybe 45 minutes, and then we will have the remaining 15 or 20 minutes for questions. Okay, so let's start. So this is a list. This is a list of contents of the talk, outline of my talk. start by discussing the question I'm going to pose in this talk. I will then give you a lightning outline, a lightning review of the so-called string framework within which I will try to present some of the answers I will try to present in this talk. The main part of the talk is going to be about a particular model of quantum gravity. And then I will end with some few comments and conclusions. So let's start. As most of you know, over the last 300 or 400 years, theoretical physicists have developed increasingly sophisticated mathematical models that now describe a vast variety of physical phenomena. We can describe supernovas going off billions of light years away. We can describe chemical reactions or nuclear reactions, all kinds of interesting things over different length scales and over different time scales. Remarkable things, in my opinion, about theoretical physics is that these varied physical phenomena that look so extremely different from each other, admit mathematical descriptions within what are basically a handful of basic frameworks. A few basic frameworks, and by framework what I mean is a sort of fundamental mathematical and interpretative structure. All the models of physics that we have today, which in turn describe this wide variety of natural phenomena. These, the incredible variety of natural phenomena that we see around us in our universe are described. Each phenomenon has its own distinct description, but each of these descriptions are have a home within a relatively small number of basic frameworks of physics. Now, two of these frameworks in my talk are the framework of quantum physics, the quantum framework, and the framework of dynamical space-time, so the general relativistic framework. So let's take a look at each of these. The quantum framework was developed a little more than 100, over a period around 100 years ago, between 1900 and 1930, roughly speaking. And as many of you know, it's the basic framework, the basic grammar that has been used in the construction of all models of particle physics over the last 80 years. It's been used for more, but in particular, it's been used. It's the basic language in which all models of particle physics are written. So let's say this in a little more detail. All modern theories of elementary particle physics are set within the framework of what is called quantum field theory. So what is quantum field theory? Quantum field theory is a framework in which you have space and time, a non-dynamical stage on which dynamics happens, where the geometry is fixed and specified once and for all, and then things happen inside space and time. Now, these things in time are described by some degrees of freedom. And the nature of quantum field theory is such that the degrees of freedom that evolve in a quantum field theory are degrees of freedom that are located at each point of space and then evolve in time. So in some sense, you have degrees of freedom at each point in space and time. One or a small finite number of degrees of freedom per point in space. Maybe more accurately per point in space. Okay? Now, of course, the number of degrees of freedom then in the quantum field theory is infinite because the number of points of space in any reasonable manifold is infinite. So quantum field theory might at first seem like a very complicated system. It's a system of an infinite number of degrees of freedom. But there is a basic organizing principle that makes it much less complicated than it could otherwise have been. And that basic organizing principle is the principle of locality. This principle asserts that 2 degrees of freedom that are separated from each other, some distance away from each other, do not interact with each other directly. Degrees of freedom interact only with neighboring degrees of freedom and then interact then with degrees of freedom far away only through their effect on the neighboring degrees of freedom interactions process. Okay, this principle of locality takes these infinite number of quantum degrees of freedom in a way that makes them subtractable. Okay, fine. So that's all I wanted to say at the moment about quantum field theories. Number of degrees of freedom. These infinite number of degrees of freedom live in a non-dynamical space-time. There are one or a finite number of degrees of freedom per point in space, and interactions are local. Right. This is the framework of quantum field theory. It's the framework all of the theories of particle physics that we're familiar with are situated. If the standard model of particle physics, for instance, is a quantum field theory. Now, the second framework that is going to play a key role in my talk is the framework of the general theory of relativity. Okay, so while the framework of quantum field theory was the home for all theories of particle physics, the framework of the general theory of relativity is the home for, in particular, all theories of cosmology. Other things as well, but in particular, all theories of cosmology. Okay, so let's get the same kind of 2-minute introduction to this framework that we had for quantum field theory. In contrast with quantum field theory, and this is sort of a key point. Well, first the similarities. Just like in quantum field theory, there's a general relativistic kind of theory, a theory based on the framework of general relativity, is a theory with an infinite number of degrees of freedom. Just like in a quantum field theory, these degrees of freedom live one or a finite number per each point in space. However, there are two major contrasts to the quantum field theory. The first one, of course, is clear from the name. The degrees of freedom in general relativity are classical degrees of freedom. They're numbers. In contrast with the degrees of freedom in a quantum field theory, which are these more complicated quantum degrees of freedom. Sort of degrees of freedom, one per each point in space. Here, they're just numbers at each point in space. The second contrast is equally important. A quantum field theory has degrees of freedom that live in each point in space and therefore time, a number per point in space. But the space and time itself in a quantum field theory is non-dynamic. Space and time sort of form a stage on which dynamics happens. Okay? The stage itself is unmoving, it's just a scaffolding, a grid to host dynamics. On the other hand, in the general theory of relativity, the geometry of space and time itself is a dynamical quantity. So as dynamic happens, the geometry of space and time evolves along with the dynamics, responding to the dynamics of matter and affecting the dynamics of the matter. So within general relativity, space and time are not spectators anymore. They're participants in the dynamics of the universe. Okay? Fine. So here we have it. We've got these two frameworks that we're going to focus on in this talk. Framework of quantum field theory, framework of general relativity, both local, both with an infinite number of degrees of freedom. Quantum field theory, the degrees of freedom were quantum, and one of finitely many per point in space. Space and time is itself non-dynamical. In general relativity, the degrees of freedom are classical, one or a finite number per point in space. Space-time itself is dynamic. Right. Now, quantum field theory, as I've already mentioned, is the basic language in which all models of particle physics are and have been written. And it has proved to be a spectacularly successful framework. In particular, the models of particle physics that have been written using the framework of quantum field theory have allowed us to predict experimental results to an astounding accuracy. For instance, I've given the theoretical, on the slide I've shown you the theoretical versus the experimental value of this fine structure constant obtained from some experiment, obtained from some theory. The details don't matter. What's important is to see that many significant digits. Digits and the agreement between theory and experiment is good to all of these significant digits, to several of these significant digits. Okay, up to these 9 here. Okay, so it's very successful, very precise, and very predictive. On the other hand, the general relativistic framework has been spectacularly successful in describing astrophysical and cosmological dynamics from scales ranging from kilometers to the size of the universe. The time delays in GPS satellites that would have affected their accuracy are described by general relativity. The evolution of the universe itself, the expansion of galaxies away from each other, and so on, is also described by the general relativistic framework. So, what do we have here? The situation at the moment is this: we've got these two different frameworks, each of which are extremely successful in their own specialized domain of applicability. Quantum field theory is successful in describing models of particle physics, whereas general relativity has been extremely successful in describing various things, but in particular models of cosmology. However, and so you might think this is a very good situation. However, there's a flaw in the ointment, fly in the ointment. The fly in the ointment goes as follows. Quantum field theory, by its construction, is a theory that is a fixed space-time manner. It's quantum, but on a fixed space-time manner. General relativity, by its construction, is a theory that used to model fluctuating space-times, but by its very nature, it's a classical theory. So you see, each of quantum field theory and general relativity, each of these two frameworks have a flaw. Quantum field theory cannot account for fluctuating spacetimes, and general relativity cannot account for the quantum nature of the world. Now we know the world is quantum, in particular the success of particle physics theory and experiment, but of course also solid state physics. Yeah, the history of physics over the last 100 years has been a very quantum history. So we know the world is quantum. We also know that space and time are dynamical. The spectacular success of the general relativity-based models of cosmology and astrophysics leave no doubt that space-time is also dynamical. But you see, neither of the frameworks that I've described to you here correctly, even at a qualitative level, encompasses every aspect of the real world that we know to be true. In particular, there is some phenomenon time are both dynamical. Neither framework that we've talked about good enough to describe such a phenomenon. This is enough. This is conceptually unsatisfactory. We cannot feel satisfied with our state of understanding of physics if for one regime it's important, but space-time fluctuations can be ignored. Another theory for another regime where space-time fluctuations are important, space-time dynamics is important, but quantum effects can be ignored. We cannot feel satisfied about it. We need something that in principle encompasses all possible situations. Pragmatic people who feel, okay, that's all very well, but really be convinced that we already have. I need an example. I need an example of phenomenon that I'm interested in, that I want to model, that I cannot do using either quantum field theory and general relativity. And in fact, there probably is one such striking phenomenon that I think all of us would agree we're interested in, and that phenomenon is the birth of the universe. So I'm going to take a couple of slides to explain what I mean. Now, as you probably know, the way we understand what we understand about the early universe goes roughly as follows. What we do is observe the universe today. So that gives us some understanding of what the universe looks like today. Particularly, we see the galaxies are moving away from each other at a certain rate, and so on. Now, understanding what things are like today gives us initial conditions for the equations of physics. If you know, in life of physics is to take initial conditions, and from those initial conditions, the equations of physics, I mean, that's their raison d'etre, their purpose, is to be able to take initial physics as input and to predict the future. But it turns out that all the fundamental equations of physics work equally well in forward and backward. You can as well take the initial conditions that we see today and use the equations of physics not to predict the future, but the past. So what we can do is to take the state of the universe as we see it now, all these galaxies rushing away from each other, and plug those initial conditions into the general relativity-based equations of cosmology, and use the equations to sort of, in our minds, create a movie of the universe evolving in backward time. What the universe had looked like before. So when we do this, we see the following. As we run this movie in backward time, we see that these galaxies that are expanding away from us now start contracting towards each other. And they go nearer and nearer and nearer and nearer to each other. The universe gets, in some sense, smaller and smaller and denser. And then there is a moment, something like 13.7 or 13.8 or 13.9 billion years ago, in which all of the galaxies that we see today are scrunched together into a very, very small region. And now nothing's really sort of getting interesting. They scrunch together in a very small region. It looks like if you keep running the movie backwards, it's going to scrunch into nothing, like into a point. And you can ask, does this happen? What happens? Do they get scrunched into a point? Does something intervene? What happens before that? And the answer is we don't know. The reason we don't know, or at least a plausible reason that we don't know, but the reason we don't know is that, when the universe is subjected to is in this very extreme state where all of the galaxies that we see now is crunched into some very small region, the equations of physics that we currently understand, the equations of physics that we're using to take these initial conditions that we have and to create this movie in our head and run that movie in back time, those equations of physics no longer apply. So the movie becomes blurry at that point because we don't know the correct equations to use to run the movie further back. When things are becoming interesting, when it looks like the universe was reaching its quote-unquote beginning, the equations of motion are not good enough to tell us the details of what happened, whether there was a sharp beginning or whether that went on forever, all of that. To be able to answer questions like how was the universe created, we need better equations of motion, and very plausibly we need equations that describe space-time that both quantum and fluctuating. That is, very plausibly we need, in order to answer this question, we need a quantum theory of gravity. Okay, so hopefully this is enough motivation for you. To summarize the motivation, we need a quantum theory of gravity to answer at least one very interesting question. We probably need a quantum theory of gravity to answer at least one very interesting question. And this question is a question that human beings have asked, presumably since they were human. How did the universe begin? Where did it all come from? So hopefully that's good enough motivation, good enough reason to motivate the study of quantum gravity, to be able to answer the questions about the birth of our universe. Great. Now that you're all motivated to try to understand the quantum theory of gravity, to try to look for a quantum theory of gravity, you could ask, well, okay, that's great motivation. How have we done? How have we actually done in looking for a quantum theory of gravity? Well, it turns out we've done very well. And the reason for this, an unfortunate practical reason. You see, it turns out that quantum fluctuations of space-time geometry are important. You know, the quantum fluctuations, the dynamical nature of space-time geometry can be important at very large length scales, like in cosmology. But for space-time to become both dynamic and quantum, that appears to happen only at very small length scales, or very high energy scales. The small length scale or the high energy scale has a name, it's called the Planck scale. It takes experiment yet constructed or foreseen that one could imagine happening in, let's say, my lifetime, probably yours, is directly sensitive to fluctuations at this extremely small scale. So to test, to prize out the details of quantum fluctuations through experiments requires building the kind of astronomical energy particle physics collider that at the moment is in science fiction. Okay, it's not an order of magnitude of 5 orders of magnitude better than what we have at LHC. It's like 18 orders of magnitude better. Okay, now, so particle physics experiments aren't going to directly give us information about quantum fluctuations of gravity and help us construct a quantum theory of gravity. What else can we do? Where else can we look for clues for what the correct quantum theory of gravity is? Well, some of you are thinking the following. If it's indeed true that quantum gravity was an important ingredient in the modeling of the very early universe, then perhaps we don't particle accelerator. Perhaps we can be clever. In the very early universe, quantum fluctuations of gravity were important. And what we could do is to take what we see in the universe now, run this movie sort of backwards, and figure out, given the state of the universe now, figure out what the quantum fluctuations of the universe must have been at very early times. Okay? But even saying it this way makes it clear how ambitious this program is. You know, a lot has happened in the universe in the last approximately 14 billion years. You know, there was decoupling of matter from radiation. There was the production of all the heavy production of nuclei. There have been creation of galaxies. There have been lots of supernovas. Black holes have collided. All kinds of things have happened in the middle. And for us to be able to disentangle all that interesting dynamics that had nothing directly to do with the quantum fluctuations in the very early universe from the thing that you're actually interested in, that very early universe stuff, it's clearly going to be a very difficult job. It's not like this idea is ridiculous. In fact, within the theory of inflation, this sense in which a little bit of this has been done. It's a very interesting program, but clearly it's not going to be an easy one. So the idea is we can try to use the detailed observations of the universe now as experimental data to help us construct the quantum theory of gravity, given the fact that quantum gravity was important in the early universe. It's a very interesting idea, but clearly not one that can be easily implemented. Okay, some of you might be thinking, fine, experiments don't work, and this idea of sort of using the state of the universe now to understand about quantum fluctuations in the very early universe is a difficult one. Perhaps what we can do is to use the fact that the universe is a complicated place, to go to a place where nature has created a situation where things are happening where a situation that's so extreme that quantum fluctuations of space-time are key to understanding the phenomena in those extreme regions. Well, it turns out that there are plausibly are such places. For instance, at the center of black holes. But as far as we can tell, every time such a crazy place exists, like the center of a black hole, or perhaps exists like the center of a black hole, it's a very hard place to access. Most of you know that black hole singularities are shielded by a black hole event horizon, which is like a one-way gate. You can walk into the event horizon, but you can't come out. You know, so if you were nasty-minded professor, send your student into a black hole to try to take lots of observations about quantum fluctuation the student might make fantastic observations, but she's unlikely to. I mean, she'll never be able to publish her results because she won't be able to communicate her results with the journal, which is sitting on Earth outside the event horizon of the black hole. So, so it's almost like there is a conspiracy. Every part of the universe in which we expect quantum fluctuations of gravity to be important either seem very hard to construct, like the particle physics experiments, or very hard to access, like the centers of black holes, or happened very long ago, like the early universe, and so hard to reconstruct. Consequently, we are constrained to embark on our quest for the quantum theory of gravity with very limited guidance from experiments, difficulty, in my opinion, in the construction of the quantum theory of gravity. Okay, so that's our situation. We seem to be in a bit of a fix. A question, what is quantum gravity, seems very important because we plausibly need it in order to construct to understand the beginning of the universe, for instance. However, we have no guidance from experiment, or very little guidance from experiment about the nature of the quantum theory of gravity. How should we proceed? To wait. Okay, this is an interesting question, but one we cannot really address now. So we'll just wait for a few hundred years or whenever until the time is right and return to this question. And that might be a sensible strategy. However, that's not how humans are. There's a question, we try to answer it now. We don't put it forward to. We're not pragmatic in that way, and that's great, right? Because you never really know when you can make a breakthrough in something until you try hard. So, I'm going to describe to you the attempts that people have made, the attempts that at least the string theory community has made to address this question given the paucity of experimental data. The way we have proceeded is by adopting the strategy of what I'm going to call the spherical cow. Okay, so what's the spherical cow? The spherical cow refers to a joke story. The joke goes something like this. There was once a farmer who had a wonderful cow who was producing a great deal of milk. But one day the cow less milk, and the farmer was very worried, and he wanted to restore the cow to health. The farmer had a friend who was a world-renowned physicist, and he thought, this guy's a smart chap. Let me call him, and maybe he can help me explain how I can get my cow back to health. He calls his friend over, and the physicist looks at the cow and says, to start, let me start with to address this problem. Let me start by modeling this cow as a sphere. At which point the farmer says, "Okay, thank you very much, but I don't really need your help." Because he realized that this physicist might write, but is not likely to have very direct applicability to his cow. So the story is a joke. But it captures, in the joke, it captures some of the essence of the way a physicist actually proceeds. When presented with a problem that is too difficult for whatever reason, physicists often take recourse to a strategy that goes like this. You simplify the problem, try to simplify it in a way that makes it easier without throwing away its essential features. And then first try to solve that simplified problem before trying to address the more complicated. Okay? And that is the strategy that that string theorists have adopted to the study of quantum gravity. Okay. The sense in which we've adopted the strategy is that the string theorists have the question of what is the theory of quantum gravity of the universe in which we live? A simpler set of questions of, can you find any theory of quantum gravity, any logically consistent theory, has all the key qualitative elements of quantum mechanics and gravity that we see in the real world? world in all details, but it's logically consistent, is quantum-like quantum theories. The real world has gravity, general relativity like in the real world, and it may have some other details different. But can you take a theory, can you understand it, can you solve it, can you learn from it? And that's the spherical cow strategy that we've adopted, that the string theory community has adopted to the study of this problem. And I'm going to tell you about it. Okay, so first, just 2 minutes of what is the string framework? Okay, not even that. Right. So let's using the string theory framework. So what is string theory? Well, this string framework is some framework, a framework of theoretical physics. I won't say anything about it except that it's a framework of remarkable power and beauty that we still understand very incompletely. It's called string theory, and the name string theory is a very poor name. It was a name adopted for historical reasons, and it's not the name that we would adopt had we to choose a name today. Trying to describe the string framework is a whole different talk, and I won't try to get into that. Okay. Now, using this framework, in 1997, a young Argentinian string theorist named Maldacena to construct what, in my opinion, is the first fully satisfactory construction, what is, in my opinion, the first fully satisfactory construction of a quantum theory of gravity accomplished by human beings. It's a toy model quantum theory of gravity. Okay, it's a theory of quantum mechanics and theory of gravity that is elements that are not true in our real world, but I'll describe it. Okay, so in the rest of this talk, what I'm going to do is to describe this one satisfactory construction of a quantum theory of gravity, the one that was essentially presented by Maldacena. And as a sort of foil to the understanding of this construction, it's useful to first recall how the same construction worked in the case of a theory of a fluctuating electromagnetic. Okay, so our goal now is to try, the goal that I have now is to try to explain to you the one satisfactory, or the class of satisfactory constructions of quantum theories of gravity, these toy model quantum theories of gravity that have been accomplished in string theory. But in order to understand this construction, in order to understand how surprising and interesting it is, I may first contrast this with an easier problem. The construction of the theory of quantum electrodynamics. So first, let's go through the review of that easier question. A question that was posed from 1928 to 1950 went as follows. Find the quantum theory of an electron interacting with an electromagnetic field. So find the quantum version of classical electrodynamics. Now, classical electrodynamics is a theory all of you know, right? Who started an undergraduate program in physics, has studied Griffiths, into our Feynman lectures, volume 2, Jackson, in which you understand Maxwell's equations in great detail, and that's essentially the classical theory of electrodynamics. The question that was posed in the 1950 is find the quantum theory of Maxwell electrodynamics. Maxwell's equations interacting with an electron field. This problem that was finally accomplished at the end of this period was called quantum electrodynamics. And in order to completely understand quantum electrodynamics, we had to understand a great deal. Great deal of ingenuity and insight went into completely constructing the theory of quantum electrodynamics. It took a long time to get all the details straight. But when all the dust settles and you look at it, from above, and you ask, in the end, what is the qualitative nature of the construction of quantum electrodynamics? The answer is very simple and almost a little disappointing. So simple that's almost disappointing. You see, classical electrodynamics, the theory of Maxwell, is a theory in which there's one or a small number of degrees of freedom. In this case, the degrees of freedom are like the E and B fields of electromagnetics. magnetism, and then maybe some other fields for the matter, at each point in space. When all the dust settles in the end, the theory of quantum electrodynamics has one or a few quantum degrees of freedom at each point in space. And there's a very tight correspondence between the quantum degrees of freedom and their classical counterparts. You see, every classical degree of freedom of Maxwell theory and the matter fields has a corresponding quantum theory, quantum degree of freedom. And there is also a sense in which the quantum degrees of freedom reduce to their classical counterparts in a particular limit, namely the classical limit, the h bar goes to 0 limit. Okay? There is a sense in which you can take the classical theory and do a sort of minimal quantization of the classical theory and produce the quantum theory. Classical theory and the quantum theory are very tightly linked. They sort of joint at the hip. You make the quantum theory by taking all the structures from the classical theory, E and B fields, and replacing them with quantum operators satisfying some conditions. Now there are many details. This is essentially the nature of quantum electrodynamics. And as you see, it's so close to classical electrodynamics that it's what you would have guessed right at the beginning. In 1928, it's what Dirac guessed. It's so close to classical electrodynamics, it's almost boring. Now I want you to contrast this with the question: what is the quantum version of Maxwell's equations? Maxwell's equations interacted with an electric field, with an electron field, is, well, for every structure in Maxwell's equations, say the E field or the B field or the electron field, you have a corresponding quantum structure in the new theory, and the quantum structure reduces to the classical structure in a particular limit. Now, in 1997, Baldwin asked an analogous question to the one we've just posed ourselves for quantum gravity. He asked the following question: what is the quantum theory whose classical limit is gravity propagating on a 10-dimensional space? In this 10-dimensional space, it has a name, it's called AS5 process 5. Now, I'm going to describe the nature of this question to you in a little more detail. But the question he asked was, so the analogy here is the classical gravity theory on ADS5 process 5 plays the role of Maxwell's equations. It's a classical theory which we know and we understand. And the question is, can you find a quantum theory that in the appropriate limit reduces to this classical theory? Dynamics is that for every classical degree of freedom, you have a new quantum degree. The answer to this question for gravity is very surprising. That for every graviton field or every graviton field strength or every Riemann tensor field operator, instead the solution was given by replacing the classical 10-dimensional fields by the solution is not given by replacing the classical 10-dimensional fields by the quantum counterparts. Instead, it's a 4-dimensional quantum field theory, and this 4-dimensional quantum field theory has a name. N equals 4, D equals 4, super Young's theory. There's a sense in which this theory lives at the boundary of ADS5 process 5. I'm not going to describe that statement. Okay? So the question, what is the quantum version? What is the correct quantization of gravity on ADS5 process 5? As an answer, I'm going to describe this in a minute to feel more. That's very different from the classical theory. The answer to the quantization is very, very strange answer. The answer to the quantization of 10-dimensional gravity theory in this funny space is a 4-dimensional quantum field theory in flat space. Now, there are many things about what I've just said, that probably make no sense to you. And unless you've heard of it before, it shouldn't make no sense to you. See, if you've been following everything I've been saying, what I've been saying sounds more or less ridiculous. You see, because the question I asked is, what is the quantum theory of a theory of gravity? So I told you that the theory of gravity is a theory in which The geometry of space and time is dynamical, whereas quantum field theories are theories in which the geometry of space and time is not dynamical. And yet, and the previous transparency, that the correct quantization of this theory of gravity on area S5 plus S5, is a quantum field theory. Isn't this contradiction? Okay. Now, the theory we started out trying to describe, this area S5 plus S5 gravity theory, is a 10-dimensional theory. It lives in 10 space-time dimensions. I told you the answer to the quantization of this classical theory. What's going on? Where do the remaining 6 dimensions go? None of this seems to make it is neither right or wrong. It sounds like it's gibberish. Let me just give you 2 slides, and it's not gibberish. I think there's a great deal of evidence that it's correct. And I'm going to give you 2 slides of how it works. Look, let's go back to the quantum field theory here. This UN, n equals 4, d equals 4, super Young's theory. There are 2 things about this theory that we're going to use. First, that it lives in 4 space-time dimensions. Second, that it is a UN theory. And the only thing about that I'm going to use is that it's a theory whose basic degrees of freedom are n cross n matrices, where n is an integer. Now, it has been known for a long time, since the time of Toft in the 1970s, that quantum theories, like just ordinary quantum field theories or even quantum mechanical theories, but let's say ordinary quantum field theories, whose degrees of freedom are n cross n matrices, develop a new simplicity when n becomes very large. And in particular, when n becomes very large, of appropriate observables in these theories become very small compared to their mean values, and the theories effectively become classical, even at non-zero h bar, even when h bar is not. Basic reason for this is the law. I mean, roughly speaking, what's going on here is the law of large numbers. Any experiment repeated n times has small fluctuations compared in its average compared to the fluctuation of any one variable. And roughly speaking, the kind of observables that we have are observables that average over many instantiations of what's happening to the basic fields. Okay, that's very crude and it's not completely accurate, but just to give you a sense. So it's been known for a long time that ordinary quantum field theories become sort of like classical in a particular limit, in a limit where n goes to infinity, when the basic degrees of freedom are n cross n meters. This basic statement has been established for a long time. However, if I gave you a particular quantum field theory whose degrees of freedom are n cross n matrices, and I asked you to take n to infinity and I asked you, is this theory effectively classical in this limit? The answer is yes. We know that, we have theorems. But if I ask you to tell me which classical theory reproduces the dynamics of this larger n theory in the larger n limit, the answer is in general we don't know. And I think that people have always assumed that for reasonable quantum field theories, the answer to this question would be not just that I don't know, it would be some horrible mess, some horrible non-local mess. So it would be some classical theory which would be so complicated that wouldn't be particularly interesting to know the answer. What other thing I discovered was when he asked the question, what is the effective classical description of this quantum field theory at the limit that n becomes very large, he discovered the answer was not a mess if you looked at it in the right way. The answer, in fact, was the equations of gravity, or type 2b supergravity, propagating on area S5 plus S5. So you see, this is how gravity emerges from a quantum field theory. We've got a quantum field theory where we've got degrees of freedom, which are n cross n matrices, where n is very large. In the limit that n becomes larger and larger and larger, the quantum field theory becomes effectively classical. However, the relationship between the classical degrees of freedom that you get out of a large n limit, that you put into your Lagrangian of your quantum theory, is not a straightforward one. It's not like in quantum electrodynamics, where there's one-to-one correspondence between your quantum degrees of freedom and the classical degrees of freedom. The classical theory that emerges out of this is difficult to understand. It requires detailed calculations, which you generally can't do. And it's very different in nature from the degrees of freedom that went into making your quantum theory. What Malvasena realized was this incredible thing. What he realized was that for n equals 4, at least for n equals 4, d equals 4 super Youngman's theory, the classical theory that emerged in the large n limit was a beautiful, simple, local theory of, however, one that was beautiful, simple, and local, not in the 4 dimensions in which the quantum field theory was originally formulated, but in a 10-dimensional space-time that was manufactured by the theory. And this 10-dimensional space-time had a geometry which was area 5 plus S5. So you see, what I'm saying here is the 10-dimensional space-time is an approximation that emerges in the large n limit. 1 over n corrections lead to quantum fluctuations of this 10-dimensional geometry. Geometry is more or less classical geometry with small fluctuations. However, if you work at some finite value of n, let's say n is equal to 5, you sum up all these 1 over n corrections and you work at a finite value of 10. By this point, we're left with the 4-dimensional quantum field theory. 10-dimensional space and time and gravity, all of which arose as in a particular parametric limit, which are precise notions only in the limit n goes to infinity, disappear when n is some finite value. Okay? As far as we can tell, area is 5 times S5, gravity plays no role in the fundamental formulation of the theory, which is just formulated as a 4-dimensional field. So within this model, therefore, there is a sense in which space-time, which is the 10-dimensional space-time of area 5 times S5, the gravitational space-time, is an illusion, an emergent notion that has precise meaning only at very large n, but whose reality becomes increasingly tenuous as n is decreased. This sounds somehow very important, and I don't want to say anything more about it, but it sounds very important. Okay, it sounds like this might be a fundamental insight into the nature of space and time in our universe, but who knows? Okay, at a much more mundane level, all of this suggests a completely unanticipated role for theories of gravity. You see, theory, Einstein's general relativity, theories of gravity were developed to analyze gravitational phenomena. And of course, they've been very successful in analyzing gravitational phenomena. But I just told you, it's something quite remarkable. I told you that if you were interested in some phenomenon, namely studying the strong coupling behavior of a quantum field theory, it has nothing gravitational in it. Okay, you want to study the strong coupling behavior of this quantum field theory. Quantum field theories by their nature have no fluctuating space and time. It's nothing gravitational in this problem. But if you are interested in understanding what happens to this quantum field theory in the large n limit and in another particular limit, some lambda goes to infinity limit, doesn't matter the details. The best way to understand this quantum field theory is as a theory of gravity in ADS 5 S5. Gravitational theories emerge as the effective classical descriptions of strongly coupled non-gravitational systems in the limit of a large number of degrees of freedom. 1 by n corrections to this classical limit yield quantum fluctuations of gravity. So this is a role for theories of gravity in a set of questions of physics that was completely unanticipated 30 years ago. Gravity can be used as a tool to answer questions about non-gravitational physics because of the ADS-CFT correspondence. Because it's often the effective classical description of large n physics for non-gravitational physics. Thus, theories of quantum gravity provide an effective large n mean field type description for several strongly coupled non-gravitational systems. And it seems likely that quantum gravity will, over the years, turn into an increasingly useful tool for studying all sorts of non-gravitational strongly coupled systems. Okay, that's it for the formal presentation part of my talk, more or less. So let me just end with a quick outlook. There are many things about the story that I've outlined are understood only partially. To start with, the fact that this quantum field theory reduces to 2B supergravity at large n has been established only using the string framework, using the magic of string theory. Now, the claim that I made that the effective large n description of this quantum field theory is given by classical equations of gravity is a well-posed claim to somebody who knows nothing about string theory. It's a claim about the behavior of a quantum field theory in a certain limit, and one should be able to directly prove it by analysis of quantum field theory. Okay, we lack a direct field theoretic understanding of this remarkable ADS-CFT duality. We do not understand in detail precisely how space and time and fluctuating metrics emerge out of strongly coupled. And it seems likely to me that we will learn many important lessons by filling this gap. Now, as I have described to you, the formulation of a single, complete non-trivial quantum theory of gravity has been a highly non-trivial accomplishment. Insights, like for instance the approximate nature of space and time, at least within those models. The string framework exerts the existence of many more such theories, many more quantum theories whose classical gravitational limits we understand. For each of these theories, we should be asking, what is the correct, complete quantum description of this system? And it seems likely that as we get more and more answers to these questions, we will learn more, we will get more and more increasing insights. Finally, in order to address questions about the birth of our universe, out of this talk that has led to quantum gravity, what we've been dealing with is not quantum gravity of the world in which we live. We've been just looking at the quantization of any well-posed classical system. Spherical cow, toy model theories of quantum gravity. In order to address questions about the birth of our universe, we would like a precise formulation of the quantum theory of gravity of our universe, the universe in which we live, not just a toy model, not just a spherical cow quantum theory of gravity. Does the quantum theory of gravity of the real world lie within the string framework? If so, where? How do we identify and understand this theory? I don't know the answer to these questions, but I think it's likely that some input from experiment somehow or the other would play a role in it. Okay, so this is the summary of my talk. First, we went through. I tried to convince you that quantum gravity is likely needed. Is the question of what a quantum theory of gravity is an interesting question, in particular because it's likely needed to understand the question how the universe began. I told you about string theory, which is an exciting but incompletely understood framework for quantum theories of gravity. I told you how the string framework led to the complete but surprising formulation of a class of 10-dimensional quantum gravity systems as lower-dimensional non-gravitational quantum systems. I told you about the case where the lower-dimensional non-gravitational quantum system is n equals 4 d equals 4 superior. I explained to you the result of quantizing of these classical theories is a great surprise. Space and time within this quantization are emergent notions. At least the fluctuating space and time, the 10-dimensional space and time, are emergent notions that have no fundamental counterpart in the formulation of the theory. There's a sense in which space-time appears to be an illusion of this fluctuating space. The complete formulation of other gravitational systems is an outstanding formal challenge. Formulation of the non-spherical Cow theory of quantum gravity in the real world is an even bigger challenge. And that's it for me.
Thank you for your talk, sir, and thank you for the lucid explanations. I really enjoyed it. To our viewers, if you have any questions, you can put them up on the YouTube live chat right now. We do have some questions. I'll just read them out to you, sir. We have Abhishek who's asking, what explanation for the dark sector does string theory provide? And whether you could explain this in a non-technical manner.
Okay, so the dark sector is a feature of our universe. String theory essentially has, I tried in my talk to distinguish between toy model theories of quantum gravity, which string theory has had great success in trying to understand. You take a simple toy model of quantum gravity, and string theory has had a great success in analyzing this. The kind of toy model that we talked about in my talk was gravity on type 2b supergravity on ADS 5 cross S5. Now look, the world in which we live is not ADS 5 cross S5. Okay, the world in which we live appears to be 4-dimensional. It appears to have a cosmological constant, but the opposite sign from ADS, positive cosmological constant, not negative one like in ADS. There's no analog of S5. What string theory has been good at doing so far is at analyzing toy model theories of quantum gravity like this, which are obviously theories of universes in which we do not live. String has had nothing particular to say, nothing concrete to say. We've not managed to use string theory to find the quantum theory of gravity of the world in which we live. This would be needed to do in order to address your question about the dark sector. So, the short answer is that string theory, as we understand it at the moment, has nothing to say about the dark sector. Maybe some wild speculations, but nothing concrete to say about the dark sector. For the simple reason that we have not yet managed to find a particular string vacuum that is a plausible candidate for the world in which we live. So sorry. So to that question, there's no good answer. Nothing. The answer is nothing to say about it.
All right. We have another question from Mukta Jyoti. She asks, what is the role of supersymmetry in the correspondence?
Okay. Excellent question. Yes. It may well, so even though I've not said it in this talk, as Mukta alludes to, in the correspondence that I described to you in this talk, supersymmetry is a fact in the sense that both sides of the correspondence are supersymmetric theories. The gravitational theory I told you about was a supergravity theory, or more precisely a supersymmetric string theory with 32 supercharges. And the quantum field theory that I told you about was also a quantum field theory with 32 supercharges. Question: every clear example of ADS-CFT, understand in clear and concrete detail, is of this form. In every clear example, the theories on both sides are either supersymmetric or very close to being supersymmetric, in sense related to supersymmetric theories by let's say RG flow. This, in my opinion, is very likely just to be a technical restriction. Supersymmetry gives you that allow you to make progress in identifying what the dual description of a particular field theory might be. Typically speaking, if you have a non-supersymmetric field theory, which may have a gravitational dual description, you just don't know because you don't have the technical ability to understand it. I believe that this is the situation, though I don't have clear direct evidence. I believe that the fact that supersymmetry, that both sides in every duality that we've seen involve supersymmetry, but it's not an essential element of this duality. Though I don't, this would be convincing only if one had a clear example of a non-supersymmetric ADS-CFT duality. But let me say one more thing about this. The kind of dualities that I've talked about in this talk are field theory gravity dualities. There's another set of kind of dualities that people have begun to understand over the last 30 years or so, which are field theory dualities. Think of this, S duality and so on. Our very own Ashok Sen played a role in understanding these field theory dualities about 30 years ago. Now, for a long time, for maybe 20 of these 25 years, or perhaps 17, for a large fraction of these 25 years, all convincing examples of field theory dualities, non-trivial field theory dualities in higher than 2 dimensions, were involved supersymmetry on both sides. And so many people began to wonder, could it be that duality is a phenomenon not of quantum field theories, but of supersymmetric quantum field theories? 7-8 years, there have been clear examples of duality between, interesting dualities between in higher than, and people will argue about this time scale. Okay, so anyway, but by now there is convincing evidence, in my opinion, that dualities of the field theory dualities of the sort that we've seen in supersymmetric theories also exist in non-supersymmetric theories, and are Bose-Fermi dualities in 3 dimensions, which by now we understand in exquisite detail in a certain window in non-supersymmetric. So this is an example of the kind of phenomenon you're asking about. In that case, at least for field theory dualities, well, most of the examples we know of involve supersymmetry. That's just because supersymmetry gives us the technical tools that we're able to use in order to establish these dualities. Where we have other tools, we find that these dualities exist even without supersymmetry. That is definitely the case for field theory dualities. I think it's likely also to be the case for field theory gravity dualities, though we don't yet have a. Yeah, okay, let me leave it. I think it's very likely. There's one more thing to say, maybe, which is that you can often take an RG flow. You can often take a supersymmetric field theory and go from there by RG flow to a non-supersymmetric fixed point. Then the supersymmetric field theory, coupled with the RG flow, would imply that the non-supersymmetric theory also has some sort of bulk dual description, but may not be easy to find what that is. And my opinion is that while supersymmetry is a technical crutch that is useful in establishing these dualities, it doesn't play a key conceptual role in the existence of these dualities.
Thank you for the explanation. We have another question from Yash Palan, who asks, is it true that for all quantum field theories that we can create, there exists a large integer n such that we get a classical theory? And can this n be generalized for all theories? And is this n unique?
Okay. Now, first part, is it true that we can always extend any quantum field theory to a set of theories with parameter n? Possibly not. For instance, this, in the context that I was talking about, n was the rank of the gauge group. And as many of you know, if you look at the set of all Lie groups, there are the classical Lie groups, which are UN or SUN, ON, and SPN, which are labeled by an integer that goes from 1 to infinity. So if you're looking at a gauge theory based on one of these classical Lie groups, then there's always this integer. Then you can view it as one of a class of gauge theories, which can be extended to a theory labeled by this one parameter set. So say you were looking at an SU3 theory, like the color theory of the real world. You can imagine that this is one of the class theories, the gauge group is SUN, and then take n to infinity. You can do that. Gauge theory examples of theories, there's no particularly natural way of doing the analog of what I was trying to do. For instance, if you look at a gauge theory whose gauge group is not a classical Lie group. For instance, E8. Say you got a gauge theory based on the group E8. E8 is one of an infinite set of Lie algebras. There's no particularly canonical way of extending that theory, endowing that theory with an integer n. Maybe more artificial ways, and this gets to the second part of the question. Is there a unique way of introducing an integer? There may be more artificial ways of doing this. For instance, introducing n flavor fields or something like that. But those things are very artificial and don't have the feel of what I'm saying. So it's not. So just to summarize the answer, there are classes of quantum field theories for which the extension of these theories by an integer n is very natural. For instance, when we're looking at gauge theories, where the gauge group is one of the classical Lie algebras, and you just replace the Lie algebra by a Lie algebra with rank n. For most other theories, there's no particularly natural way of introducing n into the problem, and if you might be able to do that, but then it's unlikely that your way of introducing it will be very unique. Yes. So it was not, sorry, I did not mean to say that every quantum field theory has a nice, interesting large N limit, or at least a natural large N limit. But classes of quantum field theories do, and when they do, the large N limit is interesting, and we've just learned through ADS-CFT might often, or maybe always, turn out to be a classical theory of gravity. Sorry to interrupt.
Yes, thank you for the answer. We have another question from Krishna. Are there any successful string theories that describe spacetime as an emergent property?
Oh, are there any successful string theories that describe space? Well, ADS-CFT describes spacetime as an emergent. N equals 4 superangles theory is a theory which, as I tried to describe in my talk, is formulated at the basic level. The formulation of the theory happens in a 4-dimensional spacetime where there is no, where the spacetime is fixed once and for all. Okay, it's not fluctuating. However, the result of that theory, okay, is string theory on ADX 5 times S5. And this is a result in a particular large N limit. So ADS-CFT, as I try to explain in my talk, is an example of an emergent phenomenon. Perhaps this was not the intent of the question. But the answer is yes, of course, string theory is full of emergent spacetime. ADS-CFT.
Another question from Shiv Shankar, who asks, what are the reasons that string theory is a special candidate in the sense that it's being pursued to a huge extent? Maybe a different framework like loop quantum gravity can provide a different insight into solving the problems that string theory is trying to solve.
Right. You know, in general, one should try whatever one can try. Now, you know, if you have, for a question like this, answers tend to become a bit less of an issue of opinion. But I'll give you my opinion. You see, when you're trying to assess the intellectual worth of an area of investigation, one way of doing it is to ask, how results has this area of investigation generated that are answers to questions that are of interest and are well posed outside your particular area? You know, how many connections does it make with other areas of intellectual activity? This, what you're doing to other people who are not interested in your questions, in your framework per se, but have their own questions and maybe open to borrowing your techniques or your results to answer their own questions. Sense, the string framework has proved. It has, as my talk was one attempt to describe such a thing. By trying to study quantum gravity carefully, we have discovered a certain unification of quantum field theory and quantum gravity that 30 years ago would have been unimaginable. In order to completely formulate a theory of quantum gravity, one complete formulation is in terms of quantum field theory. Or said in a reverse way, if you want to understand the effect of strong conflict behavior of quantum theories of certain quantum field theories, the answer to that question is obtained in terms of a theory of quantum gravity. So suppose you were a condensed matter physicist who didn't care at all about gravity, but wanted to know, but had a system of strongly interacting electrons, how to model the system. The answer to your question may well, because of string theory, because of the insights of string theory, the answer to your question may well be that the best way of understanding your system is by using the equations of gravity in some emergent extra space. Remarkable thing. gravity is turned into a tool to answer questions about non-gravitational physics for physicists who have no particular interest in gravity per se, but are forced to use gravity to answer the questions they are interested in, because gravity emerges as an approximation to questions about non-gravitational physics. This is an example of connections that happen that suggest that there is a certain vitality in the field. Okay, there are many other connections like this, including connections to mathematics. The fact that the string framework, this powerful framework, makes all these, unifies different areas of physics in this incredible way, and makes connections also then to interesting areas of mathematics. And here is something nice. What I would say about string theory. The question also mentioned loop quantum gravity. I know very little about loop quantum gravity, but so that question should be posed to somebody who's a loop quantum gravity expert. I won't comment on it, except to say that people should feel free to pursue all kinds of ideas. Then something good will come out of it. I mean, this is not a either-or question. People should feel free to pursue every idea they have, and then let 1,000 flowers bloom, or was it 100 flowers bloom? I can't remember. Okay, end of my answer.
So you spoke about connections between different fields of physics. Some of your previous work was on the connections between the equations of fluid dynamics and Einstein's relativity.
Yes.
Could you explain your work?
Sure. I'll give you 2 minutes about it. The ADS-CFT correspondence, as I explained to you, a certain limit. The classical equation, the effective description of a quantum field theory, becomes the equations of gravity. The claim becomes a classical equation of gravity. However, there is a much older claim, actually 100 years older, 200 years old in some sense, which is that in a more limited set of circumstances, the effective description of almost any reasonably opposed physical system should be governed by another set of classical equations, namely the equations of hydrodynamics, equations of fluid dynamics. Now, if both these statements are true, then that there must be some sense in which the classical equations of gravity in ADS5 comes as S5. It's those limits that correspond to the limits that would appear within which the field theory admits a hydrodynamical description. So that the classical equations of ADS5 of gravity on ADS5 times S5 should reduce to the 4-dimensional Navier-Stokes equations. Okay. For both these statements to be true, it seemed to us like this must be the case. So we looked at this question, but then by direct analysis of the structure of Einstein's equations in ADS5 times S5, we showed this was true. Now, what we got was the Navier-Stokes equations, but the relativistic Navier-Stokes equations, because we were dealing with a relativistic quantum field theory. And the relativistic Navier-Stokes equations have some parameters, some in the equations. And one of the things we did in our papers, and other people also did this, we worked out specific equations of fluid dynamics that you got. Okay, so what this established, by the way, was that equations, particular dynamics, there is a one-to-one correspondence between solutions of these hydrodynamic equations and particular kinds of solutions of Einstein gravity. The equations of Einstein gravity and AS5 plus S5. So it was like a classical unification of what may be the two best studied partial differential equations in physics, namely the equations of fluid dynamics and equations of Einstein gravity, though only in particular limits. Okay, now this was good. This was already nice, in my opinion, interesting. But then something, really interesting happened, which was this. When my students and other people repeated the calculations we did to include not just the stress tensor, but stress tensor and charge, hydrodynamics with charge associated with it. They got new equations of hydrodynamics, and these equations were published. And then after the equations were published, we got an email from a well-known physicist, a guy named Son, who contacted us and said, roughly speaking, very politely, roughly speaking, that the answer you got sounds very interesting, but it can't be right because your equations, the equations of hydrodynamics that you presented in your paper, do not fall within the accepted framework, within the allowed set of equations of hydrodynamics listed by Landau and Lifshitz in their text on fluid dynamics. And then this led to a sort of back and forth. And the end result of that was a paper by Sohn and Soroka, where they understood that the resolution to this contradiction was that Landau and Lifshitz had messed up. Under certain circumstances, the framework for hydrodynamics that had been, I think, widely accepted over 100 years was incomplete. It could be broadened, in some cases needed to be broadened. And once you did that broadening correctly, the equations that you got out of gravity bang fit the right framework. So this is, in my opinion, an example. I've said this in so much detail. It would be because I think it's a great example of what I was trying to say earlier on. Suppose you were a guy, a physicist who does not care at all about gravity, but you want to understand the equations of charged relativistic hydrodynamics, for instance, to model the Rick experiment in Brookhaven, or to model the heavy ion part of the LHC experiment in CERN. You don't care about gravity at all. Gravity is not your cup of tea. It's not your physical interest. Nonetheless, to get the way that we've arrived at the correct framework for the equations of hydrodynamics that model this charged relativistic hydrodynamics, the path for that, gravity and the ADS-CFT correspondence. For about 100 years, people got the basic framework, in a small way, but still in an important way, got the basic framework of charged relativistic hydrodynamics a little wrong. And that was fixed up only by using gravity and the ADS-CFT correspondence. This is an example, I think, of a way string theory impacts experiment, very indirectly. Well, I'll say one more sentence and then stop. Physics is full of claims of the following nature. In any reasonable quantum field theory, such and such and such must happen. Oftentimes, it turns out that these claims are not tested. Now, if there is something true about any quantum field theory, it should be true about specific quantum field theories. Using ADS-CFT, we have exquisite control over some quantum field theories. And you can take these claims that people make and test them. And my experience, 1 out of 2 times that you do such a test, you find that these claims are, well, not quite wrong, but not completely correct. Not completely correct. You can look at that claim again and correct it. Once you've corrected this claim, the corrected claim is corrected just using the basic principles of quantum field theory. It applies to every quantum field theory, not just the one that you could model using the one that you could solve in detail using ADS-CFT. Sorry, this is a long answer. The end of my answer.
Thank you, sir. We'll take the last question. It's by Shubham. He asks, is there any progress regarding a quantum version of the equivalence principle?
Is there any progress regarding quantum version of the equivalence? Well, I'm not sure what the question is asking. At a very naive level, the equivalence principle should apply quantum mechanically as well as classically. But perhaps the questions are more sophisticated. You see, within general relativity, quantum, sort of at the heart of the equivalence principle lies the following statement. For every geodesic observer, in short, the rules of physics are the same. If you're moving along a geodesic, you're in free fall, in your little local Einsteinian elevator, the rules of physics are those of flat space. relativity, and they're the same. So is that statement true also for quantum mechanics? And for short regions of space as well as time, certainly that's true. Question about whether the rules of quantum mechanics apply in an exact way for all observers, including those that cannot go on for an infinite amount of time. You see, in presence of black hole, for instance, some geodesics end up at black hole singularity. And it's not totally clear that the rules of quantum mechanics should apply unchanged to such observers, because they end in a finite. So, so the answer to my to this question is I'm not completely sure what the question is. If the question is a naive one about local in space and time, as far as I can tell, the equivalence principle holds as well quantum mechanically as classically. If it's a more sophisticated question involving subtleties, I think the answer is not totally clear.
All right.
Yeah.
Thank you, sir. That was the last of the questions. Thank you for your time and thank you for the amazing talk. I hope all the audience have learned something new today. Thanks to Vyom, Parvati and Muskan as well for handling the technical details of the talk. It was a pleasure to have you, sir. Thank you so much.
Okay, thank you for the invitation, and hope all of you are doing well in these strange times and keeping up your enthusiasm and staying excited about learning physics and science.
Thank you so much, sir. We'll see you all in the next episode of SciTalks. Goodbye.